Hey, what's going on, guys? It's Jenkins. I got here with me Omero, Stretches, Juan Segura, Javier, Dominic Diaz, Big Chungus back there, and my boy, baby Mick Deanda. We're going to go over our first video lesson. It's what we've been talking about for the last week. It's series circuits and what we call Ohm's Law. So I wanted to start you off by talking about the three parts in Ohm's Law: current, voltage, and resistance. All three of these are found in the simple series circuit, and we're going to learn how to work with them today. So first of all, voltage, right? Voltage is going to be the charge, right, that pushes from the battery all the way around the circuit, right? It causes the current to flow. So inside of a battery is this electric potential, and the difference between the positive and negative terminal is going to make the electricity want to flow around this juicy circuit. That's our voltage, right? So what are some sources of voltage? You guys already know. Batteries, right? Like in your smoke alarm, your batteries like in your phone, batteries in a flashlight, or a generator, something that generates electricity. We'll talk about how that happens in the next lesson. Outlets, 120 volt outlets that are in your houses or here at school to charge your laptops. Jared, laptop charger. These all provide sources of voltage, right? And our symbol for voltage is V. V for voltage, right? So where does voltage come from? And the units are, of course, volts. Voltage comes from a dude named Alessandro Volta, an Italian physicist, played with batteries, unique guy. Look him up if you want, but that's where the word volt comes from. Next up, voltage at home. So your power at home is 120 volts, right? So where does that power come from? From power plants. It gets carried through high voltage power lines into your house, and it gets stepped down with transformers to where you can use it. This is what powers your little Xboxes, your TVs, your video games, your computers. It charges your phones eventually, and that's how you use voltage at home. Now, current. When we're thinking about current is the electricity that gets pushed around by the voltage. When I put the battery in, boom, then current can flow, right? So we're going to call current the flow of charge, right? The electrons within a conductor that go through the entire circuit, right? So this is the current. And charge is only going to flow if there's a voltage source or a potential difference. If there's no battery there or outlet, no current is going to flow. No current is going to flow through the circuit. I'll show you what that means in a second. The symbol for current isn't C, however. It's I. I is the symbol. And the unit is the amp. You might have heard of amps before, right? So amps is named after this dude, Andre Ampere, right? He's a French physicist. You get the point. All these physicists get to name what they come up with, right? And the unit of measurement for voltage is the amp, named after this dude. So we've got voltage, volta, ampere, amps. And next up, right? How about, let's talk about, current for just one more second. Is current dangerous? Yes, it is, right? Current is actually what kills you, not the voltage. Our Van de Graaff generator right here, well, it generates very high voltages, but you saw that it was static electricity and it couldn't kill you, right? Because it doesn't have a lot of amperage. So let's look at some amperages that can kill you, right? So 0.001 amps, that's going to hurt. It's going to sting a little bit. 0.005 amps, that's painful, right? 0.01 amps is going to lock your muscles up. This is when you see videos of people getting tased, or the cops tase somebody and they go like this, and they're going like this, and their legs are like, that's because there's a lot of amperage, at least 0.01 amps. Next up, 0.015 amps, that's when you lose all your muscle control, right? You can't move a muscle. And then anything past that, over 0.070, is probably going to kill you, right? That's less than 0.1 amps to kill you. That's not a lot. So let's talk about the next part in a circuit. It's the resistance. We talked about the voltage, the potential difference that's going to move the current. We talked about the current, right, in amps. Let's talk about what slows it down, and that's the resistance. Now, resistance is going to oppose the push of those electrons from the potential difference, right? From the voltage source, it's going to slow down that electricity. It affects the speed of the current. Resistance slows it down. So our symbol is R, and the unit isn't R, it's an ohm. And ohms is not O, but this little symbol right here. This symbol that looks like an upside down horseshoe is the Greek letter omega. You might have seen it in a comic book or a TV show, but it's just a Greek letter for O, right? And this stands for ohms. Guess who this is named after? A dude named Georg Ohm. Georg Ohm, right? He's a German physicist. Yes, all these dudes are physicists. And knowing now that we have ohms for resistance, current in amps, right? And voltage, V for voltage, we've got the complete, what we call Ohm's law. We've named it after this dude right here. So let's talk about voltage and current real quick. Voltage and current is directly related. So if the voltage in a circuit increases, the current increases, right? That makes sense because the more electrons I push, the more they go around in the circuit, right? So if the voltage decreases, the current decreases as well. You can see then this is a direct or proportional relationship. The more current you have, or the more voltage you have, the more current you have, right? You want more current? Use a bigger battery, right? Less current? Smaller battery. Or add in some resistance. So resistance and current is the opposite, right? If the resistance increases, the current decreases. That makes sense, right? If you block more of the electrons, less current can flow. And by the same token, if you lessen the resistance, more current can flow. So this is a inversely proportional relationship. The higher the resistance, the lower the current, right? So this is called Ohm's law. And it's very, very simple. You've got to know it. Here it is right here. It's going to be the relationship between current, voltage, and resistance. And it's named by Georg Ohm. And here it is. V is equal to IR. And this is going to be simply my voltage going to be equal to my current times my resistance. That's it. If you can multiply and divide, you can do Ohm's law. It's very similar to other 3 variable formulas that we've had in the past, like F is equal to MA. It's super easy. And voltage and current are directly related, and this R, resistance, is inversely related. The higher the current, right? The higher the voltage. The higher the voltage, the higher the current. The lower the voltage, the lower the current. But the higher the resistance, the lower the current. Resistance impedes the current flow. So let's see how this works. Mathematically first, and then we're going to put it in a simple circuit and we'll be done. So, how about this? If you want to find the resistance in Ohm's law, hold on, let's do some examples. We'll just go straight to the examples. So, let's draw a simple series circuit. And remember from our lesson last time, series because they're in a line, right? There's only one path for the electrons to flow. Let's start it off. I'm going to start with, does anyone know what I start with? What do I start with when I'm drawing a circuit?
Battery.
Battery. Good old metal. I'm going to start with the battery. One big line, one small line. What does the big line and the small line stand for?
Negative and positive.
That's right. Positive and negative. And my electrons are going to want to flow from negative to positive. It's going to be a potential difference between here and here. That's going to cause that pressure that's going to push that electricity, right, at the speed of light. That energy is going to move and do work. So I'm just going to draw a simple circuit right here. Yeah, like this. Now, this circuit right now is complete. It's probably energized. There's some current going through here. And let's give this battery a rating of, let's say it's a car battery and it has like 12 volts in it, right? Well, there's nothing in this circuit right now. Let's put a couple things in there. Let's put some resistors in there. Let's do it. How about a resistor here, a resistor here, and a resistor here, right? So this, all these adds resistance to the current flowing through the circuit, right? So do you think the current is going to go up or down after the current goes through these resistors? Do you think it's going to go up or down?
Down.
Down, right? You think. Let's see. How much do you think this, let's just pick a number. This one, let's, 2. 2 what?
Volts.
No, this volts is battery. That's the charge.
The I.
2, I is current. That's what's flowing around. This is a resistor.
It's the R.
R. So what's the unit for R?
The capital R.
No. What's the unit? Like inches, feet? What's the unit for ohms?
The omega.
Omega, yeah. So that's ohms. So that's a 2 ohm resistor. Let's make this one also a 2 ohm resistor. And let's go ahead and make this one a 4 ohm resistor. So a couple questions for you. What is the total resistance in this circuit? Also known as the equivalent resistance. What's the equivalent resistance, also known as the total resistance of this circuit? It's super simple, isn't it? What do? The total resistance of this circuit.
Add it together.
I add it together. Well, what is it? Someone tell me.
8.
8. 4, 5, 6, 7, 8. The equivalent resistance is 8 ohms. Now, my question to you then is, what is the total current? How many amps of current is flowing through this circuit? So, how much current is flowing through this circuit? How would I figure that out?
By adding it.
By adding what? I have my voltage source. It's pushing current through here. I've got the current going through these resistors, right? I know the resistors are 2 ohms, and 4 ohms. Well, what is the current? How many amps of current is going through this circuit right now? How could I figure that out? What did we just see?
The formula.
The formula. Ohm's law, which is what? Tell me. Tell me. V equals?
R.
Huh?
Something R.
Something R?
IR?
IR. V stands for voltage. I stands for current. R stands for resistance. How much is my voltage? 12. How much is my current in the circuit? That's what I'm trying to figure out. So I'm going to leave that variable here. How much is my resistance? My total resistance. The equivalent resistance is how much? Stretch has already told me. It's 8. Now I have this simple formula, and I'm going to move this voltage over here. 12 is equal to I times 8. The voltage is equal to current times resistance. 12 equals I, the variable, times 8. I times 8 equals 12. What can we put here to make this true? What does I equal? Let's do the simple algebra. All I have to do is divide both sides by 8. That cancels out. So I is going to equal 12. Divide by 8. So I is going to equal what? If I simplify this, what do I get? Somebody hook it up. Calculate it. 1.5 what? The current is 1.5 what?
Volts.
Huh?
Volts.
No! Volts is the battery. We already know the battery has 12 volts. We're not talking about the battery. We're not talking about the resistors. We're talking about the current. What is that unit for current? That's for the resistance. The other one. The other one. Current. Voltage. Ohms. What is the current measured in? It starts with the A. Amps. Our current is 1.5 amps. 1.5 amps. Now, the last thing I want you to see. The current is going to come through this circuit, right? And go through this. Now, the voltage is going to be shared from here to here to here, right? The current's going to be the same throughout, but the voltage is going to be shared in each one of these resistors. This voltage is going to be shared by each one of these resistors. So, if we wanted to find out the voltage at any one of these points, all I have to do now is use V equals IR to do that, to find the voltage at any point. Right here it's 12, but from here to here, it's not going to be 12. And from here to here, it's not going to be 12, and it's not going to be 12. But it's all going to add up to 12 eventually. So we already said the current is 1.5, so we know in this entire circuit, the current, I, is going to be 1.5 amps. So what is the voltage here? All I have to do is calculate using V equals IR. The voltage is going to be equal to the current, 1.5 amps, times the resistor, 2. I want you to tell me, stretches real quick, or Jared, what is 1.5 times 2?
3.
3. So the voltage is 3 volts. How about this one? Let's do this. So the voltage here is going to be my total current, which is 1.5 times 2. What is 1.5 times 2?
3.
3. So the volts here is going to be 3 volts. How about this one? I want to know the voltage there. 4 ohms of resistance times the current of 1.5 What is 1.5 times 4? Calculate.
6.
6? 1.5 times 4 is? Check him.
6.
6 volts. Now, what do you notice? 6 volts, 3 volts, 3 volts. Add them up. 6 plus 3 plus 3. What do you get? Huh?
12.
12 volts. All of these resistors share the voltage. We have 3 here, 6 here, 2 ohms resistance, 2 ohms resistance, 4 ohms resistance. The total circuit has 1.5 amps. We solved it through this one little powerful equation. V is equal to IR. Ladies and gentlemen, this is a series circuit using V equals IR. Remember, voltage is the potential difference. It pushes the current. Current is the amount of flow measured in amps. Resistance is impeding that current. That's measured in ohms. V is equal to IR. We can calculate no matter what. This is it. Use this right here that I just showed you to answer the next 5 questions, and I'll see you next time. Boom. Hit like and